Okay, so today we are going to start lecture set number 6. Might even finish lecture set number 6, and then we will get into lecture set number 7. Lecture set number 6 is a continuation of lecture set number 5. So in lecture set number 5, we discussed the process of fitting, interpreting, and evaluating the logistic regression model, in particular, the simple logistic regression model. So when I say simple, I just mean the logistic regression model where you only have one explanatory value. When we evaluated the model, we used the deviance, which is reported as the residual deviance in R. So this is a value that we also learned how to calculate, or at least a value we learned how to find in R when we worked through the lab material yesterday. What we're going to do today is introduce a number of other model evaluation criteria, and we will use them to test hypotheses about the fit of the model. And we will also use them to compare the different types of binomial GLMs to one another. So there are a number of different outcomes, I guess you could say, or like a number of different applications of these criteria. And I think that one of the most important applications is model comparison. So while, again, we can get a sense of if the model fits well using the deviance, it's also helpful to be able to compare our fitted model to other models to try and get a sense of how that model is performing compared to other potentially useful fits. All right, so we're going to talk about a number of different statistics, R-square type measures, likelihood-based measures, residual analysis. Then I'm going to come back to a point about the deviance and how the deviance can be somewhat misleading, even if it does give evidence that the fit is sufficient compared to the maximal model. And then we will take all of these measures and kind of and put them together and use them to compare the different types of binomial GLMs that are readily available to us via R. All right, so as a refresher, in lecture set 5, we studied the simple logistic regression model. Again, when I say simple logistic regression model, I mean the model that only has one explanatory variable. This is a special case of the general logistic regression model. So the same way the SLR model, the simple linear regression model, is a special case of the MLR model, the multiple linear regression model. Any logistic regression, the logistic regression model with one explanatory variable is really a special case of the general logistic regression model, where we can model the log odds of some event given p explanatory variables, which is what the second model is highlighting. So we have boldface xi, which is representing your n by p design matrix, and beta, which represents your vector of model parameters. Okay. The general logistic regression model can be used when the response variable yi is binomially distributed. It can also be used when the response variable is Bernoulli distributed. So this model is quite flexible in terms of what we can use it to do, whether that be predict the probability of some outcome and then estimate the expected number of values that would meet the criteria, or in a more simple sort of classification setting, we can use it to predict the probability of an outcome and then use that to classify a value as being either in this class or not in this class, for example. All right. I mentioned before, and we looked at an example of this, that the deviance is typically the primary model evaluation statistic. So we can think of the deviance as a goodness of fit statistic. One of the benefits of using the deviance is that it is chi-square distributed on n minus p degrees of freedom. So given that, asymptotically distributed. So given that we have a large enough sample size, we can use this relationship with the chi-square distribution to test whether or not the fitted model is sufficient compared to the Maxwell model. We'll also see another style of test today where we can compare the minimal model to the fitted model. And we'll also see, and we also know that the deviance can be used to compare between two models where one is a subset of the other. Okay, so the first goodness of fit statistic that we will introduce is the Pearson chi-square goodness of fit statistic. So this has a pretty familiar definition. It is a chi-square random variable, same as the deviance, and it's found by taking the sum of the observed minus expected quantity squared over expected. So I would imagine that this looks fairly familiar to all of you because this is the general definition of the chi-square test statistic. In the case that we have a binomially distributed random variable, we can write the chi-square test statistic as follows. So first off, if O is equal to yi and E is equal to ni pi I, then x squared is equal to the sum of the pi I is equal to the sum of the yi minus ni pi I squared over the ni pi I. All right. So this can be, and we can simplify this and show, well, this is actually where I was going to end. So we can show that in the case that O is equal to yi and ei is equal to ni pi I, this chi-square test statistic can be written as follows. And then if O is equal to yi and E is equal to ni pi I hat, then the chi-square can be written as yi minus ni pi I squared divided by ni pi I. And this second representation is the one that we will use in practice because we will usually be estimating the pi i's based off of our binomial model. Right. Let me make sure. Yeah. Right. So the chi-square value and the deviance are actually asymptotically equivalent. So basically, for a large enough sample size, they're both going to have the same distribution. And they're actually going to be very similar in value. So the chi-squares test statistic and the deviance, maybe you might say it's redundant to use both, but the chi-square value does give us another model fit criteria that we can use to evaluate our fitted model. And we can use this in the exact same way that we did we can use it in the same way that we do the deviance. Just like with the deviance, if the sample size is small, these values become less reliable, in particular if the response variable is a Bernoulli. So this is a situation where the case count for each observation is only 1, then neither of these values are particularly effective. One of the things that isn't entirely clear is I keep mentioning this idea that for each observation, you have to have a large enough sample for these distributional properties to be appropriate. The question one of the natural questions that might come out of this is like, how many observations do you actually, or how big does little ni need to be for each observation in order for these values to be reliable? And I think that while there isn't really a hard, fast rule that I've been able to find to answer that question, the illustrations that we've been looking at so far, for example, with the beetle mortality data, we've had sample sizes that are greater than 50 for example, and those have been illustrative of those have illustrated situations where we have been able to use the deviance reliably. I've seen estimates where it's something like the trial number for each observation has to be greater than 10 in order for these values to be reliable. But an exact hard fast rule, like one that you would find from the CLT, isn't something I have come across yet. So that is something that's worth looking into as we progress through the course. And if you're interested, it's something that you can explore. And if you find a solution, I'd be happy to hear it. Okay, so you'll probably recall for regression models that the R-square is a very popular type, a very popular tool for evaluating the fit of the model. So we typically look at values like the R-square, or in the MLR case, the adjusted R-square. There's two different types of R-square-like measurements that we will utilize in this course. The first one is shown here, so I'm calling this one the pseudo R-square. So the pseudo R-square is the likelihood at pi hat given y minus the at pi tilde given y minus the likelihood at pi hat given y. In this illustration, pi tilde represents the estimate of the model parameter for the minimal model. Okay, so pi tilde is estimate from, or for rather, minimal model. Okay, and in this case, when I say the minimal model, what I mean is the model logit pi I is equal to beta 0. So the minimal model is the model with no explanatory values in it, just logit equal to a constant. All right, and pi hat is going to be the estimate from the model of interest, so from whatever model we're exploring. Okay. So pi hat is estimates for fitted model of interest. Okay, so this R squared is basically the improvement in the log likelihood function due to the terms in the fitted model compared to the minimal model. So it's not, with the original R squared, which is the value we would use in SLR and MLR, that model reflected basically, or was an indication of how much variation is being explained by the fitted model. So it had a very nice interpretation. We could basically compute the value and say, this percentage of the response variable is explained by the model, because it was a ratio of the variance of the model, or it was a ratio of the sum of square for the fitted model over the total sum of square in the entire experiment. This particular measurement is an R squared type measurement because of the construction. So it's taking, it's taking a difference between these two likelihoods, and then it's standardizing it by the minimal, or by the log likelihood for the minimal model, which is going to be greater than the log, or should be greater than the log likelihood for the fitted model. I think in every situation it will be. Anyways, so what this is basically is the difference in those log likelihood values divided by the larger log likelihood. So it represents it's a representation of how much larger the maximized log likelihood is for the fitted model compared to the minimal model. And I suppose in that sense, you could think of it as a representation of the amount of additional I don't want to use the word information. Well, I think the best way to think of it is the representation of how much the log likelihood as it has improved compared to the minimal model. Okay. And it's not really all that different from just taking the difference between the two and being like, we gain this many units. It's just that we're standardizing it between 0 and 1, essentially. Right. One of the things with the pseudo r-squared that makes it a little bit less valuable is it will increase as we add models into, or as we add parameters into the model. So it suffers from the same drawback as the r-squared, but we could use it to compare, we can use it to compare different types of binomial GLMs that are being fitted using the same explanatory space. So it does serve, it is useful as a model comparison criteria when you're using the response as a function of the same explanatory values, and then we're changing, for example, the link functions in each of those situations. All right. Any questions about that? Okay, so there's another type of r-squared measure that we can utilize to compare our models. Similar idea to the original measure. We can call this, I call this the r-squared subset D measure. So this is an r-squared based off the deviances. So you can see here what we have is 1 minus exp d minus d null. So again, here, this is deviance for the minimal model. And this is D for fitted model. And it's a very similar idea. Like basically what we're doing here is we have a representation of how much we have a representation of the improvement in fit of the fitted model compared to the minimal model based off of a transformation of the deviances. So like with a traditional r-squared value, this value is standardized to be between 0 and 1, and we can say that we can say that the models that have values closer to 1 would indicate a better fit. Okay, so in this case, we have, compared to the previous approach, we have a boundary that represents, something like a perfect fit. So if the r-squared d is equal to 1, that would indicate a very good fit compared to the minimal model. And again, the nice thing about the r-squared d compared to the pseudo r-squared introduced on the previous slide is we can use it across different modeling types to get an idea of how the models are fitted compared to the minimal model. All right. Okay, so those are the 2 r-squared type measures that we can utilize. Now we're going to talk about a suite of different likelihood-based approaches. The first method, or the first tool that I'm going to introduce is called little c. So capital D compares the fitted model to the maximal model. Little c compares the fitted model to the minimal model. Okay, so it's kind of like, it's labeled C sort of on purpose. If D is compared to maximum, now we're going to compare to the minimum. So we're going to move down. Let C represent the value, but the letters are in some sense arbitrary. It's the functionality that really matters in this case. So again, under the assumption that the parameter that maximizes the likelihood for the minimal model, or given that the parameter that maximizes the likelihood for the minimal model is pi hat, which is formally defined here, we're going to let capital C represent the 2 times the difference in log likelihood values between the fitted model and the minimal model. We can, in the case of the binomial, or in the case of the logistic regression model, we can actually show that C is going to have the value given here. But we can easily compute this for other types of models as well, because we can easily find the log likelihood values using the R output, or using R output. Nonetheless, so we can find C, and then we can use C to test whether or not the fitted model is required compared to the minimal model. So our deviance allows us to test whether the fitted model is sufficient or if the maximal model is required. With C, what we're going to do is test if the minimal model is sufficient or if the fitted model is required. Okay, so it's two different types of tests, and both can give a suggestion about whether or not we need that, whether or not the fitted model is valuable to us. All right. Now, in this case, C is going to have a chi-square on P minus 1 degrees of freedom. Right? Where oh, yeah. Chi-square on P minus 1 degrees of freedom, where P represents the number of parameters of the fitted model. And that would be consistent with the definition of P that we had for the deviance as well. So I'll just make a note there. And that would make sense because the value C is the difference between the fitted model and the minimal model. So when we're computing the DF, since they're both, when we're computing the DF, we're basically saying the degree of freedom for the fitted model, which is n minus P, minus the degree of freedom for the minimal model, which is n minus 1. So we would have n minus P minus n minus 1, and we would end up with P minus 1 in that case. Yeah. The n's cancel out, and then we have negative n, negative P plus 1. So let's just trait sneakiness with this. Okay, so that's our first test. We can use that test in the same way we did for the, or we can use that test to test whether or not the fitted model is required, but the result of the test would be actually rejection would indicate the fitted model is required, whereas with the deviance, its lack of rejection indicates that the fitted model is sufficient. There's two other likelihood-based criteria that we can discuss. Both of these criteria are really only useful in the case of model comparison. So on their own, they don't give a lot of value because there's no, they don't have, unless you have multiple models, there's nothing you can compare them to. So for example, we have seen the AIC in the context of stepwise regression or backward elimination or forward elimination. In that context, you start with a maximal model or a minimal model, you get an AIC, and then you add or remove a variable based off improvement in the AIC. But improvement is with reference to that starting point. The BIC is the same idea. It's just a strict, the penalty that it applies is more strict than the penalty that's placed on the AIC. So both of them need a reference. So again, these two criteria are best utilized within the context of model comparison. And one of the things that's great about these criteria is that we can use them to compare across link functions within the same family. We could use them to compare across, and we could also use them to compare across different types of GLMs fitted to a response variable given the same set of explanatory variables. And then following from the AIC, and then following from the stepwise procedure, we could also, we should be able to also use them to compare across subsetted models within the same family, because we're, in the case of forward and backward elimination, we are calculating improvements in fit using the AIC. So that would imply that we could use them to compare, say, a binomial or logistic model with x1 and x2 to the same model with x1. Okay, so I'm going to go through the calculation of these different statistics now. So we'll see some illustrations of, I think, yes, perfectly. So I'll show you some illustrations of how to calculate these different values for the same beetle mortality data set that we've been using, that we use in lecture set 5, and has kind of been our illustrative data set for the logistic regression model. At the end of the lecture, we're going to talk about fitting the different binomial GLMs, and we will see a different data set in that case. So there will be a little bit of a switch up coming. But for now, I'm sure you guys can recall, so our beetle mortality data, we have our dosage level, and then we have the proportion of responses on the Y, or we're modeling the number of successes as our response variable. So that's binomial. We've graphed on a couple of occasions the scatter plot showing the proportion of beetles killed as a function of the dosage level. We fitted a logistic model to this data set in the previous lecture set and in lab yesterday. So some of the summary statistics from that fit are shown below. So the log likelihood of the fitted model is negative 186.235. Remember that this is not including the combination term. So this is the, I guess, unadjusted log likelihood value. And then the deviance for the fitted model is 11.23. That fitted model has equations shown below. And then I have information from the minimal model given as well. So we have the 0.42630, and then we have the log likelihood for that minimal model. Again, this is unadjusted, and we have the deviance for that minimal model as well. Okay, so let's look at a couple of illustrations here just to get some practice with computing a few of these values. So we'll start off with, I guess we can go in order. So we can start off with that pseudo r squared term. Okay, so the pseudo r square is equal to the log likelihood of the fitted model given the data minus the log likelihood of the minimal model given the data divided by the log likelihood of the minimal model. Oh no, I have this backwards. Sorry. There we go. Okay, minimal minus fitted divided by minimal. Okay, so then from the previous slide, this is going to be negative 322.7205 minus 186 0.235 divided by negative 322.7205. Okay, so I'm just going to make sure I have the right number recorded here. Okay, so this is 0.4229. Right. So, and this is essentially showing us that the between the fitted model and the minimal model, the log likelihood value is increased by roughly 42%. So it's 42% higher than it was under the minimal model. All right. So the next thing that we can look at are those deviance values. I'm just going to make sure I have these things. So we have r squared d. So this is going to be 1 minus exp of d minus d null divided by little n divided by 1 minus exp d null divided by little n. Sorry, I just want to make sure I'm not watching this formula. So I was missing a bracket before. I knew there was, there we go. And then this goes here. Okay, so I was missing, there we go. So this whole thing is inside the exponent. Good thing I caught that. All right. Okay, so then going back to here, we're going to have 1 minus exp. And then d was 11.23. Minus d null, which was 284.208, 202. Divided by, and then here we have 481. So if we go back and look at the little mi here, the little n we are using in the deviance calculation is the sum of these values. Okay. All right. And that should give us zero point 971. And this would indicate that the model is fitting really well, obviously. It's very close to 1. The one thing I find with these two values, like, so the pseudo R squared tends to be quite low, and with the R squared D, it tends to be quite high. So again, this does imply that the fit is quite good with reference to a value of 1. But these, I think that, again, the value of these criteria is really within the model comparison set, because then we have different values to compare to, and that helps us to establish a more realistic criteria for the problem at hand. Okay, so those are the two R squared values. Let's take a look at a few of the other quantities here. So I'll do the C next. All right. So C is equal to 2 times the likelihood of the fitted model given the data minus the likelihood of the minimal model. Right. Right. Okay, so this is going to be 2 times, and then we have negative 186.235 minus negative 322.7205. And this is equal to 272.970. So here we have H0, minimal model is sufficient versus HA maximal, or sorry, fitted model is required. So then on S2, if we declare a 5% significance level, then on step 3, we're going to have C is equal to 272.970. Okay, so on step 4, we would have a chi-square on 0.05 and p minus 1, which is a chi-square on 0.05 and 1 in this case, because the fitted model has 2 parameters, beta 0, beta 1. So 2 minus 1 is 1. Okay, so a chi-square 0.05, 1 degree of freedom, I believe, is 3.84. Right, so this is clearly well within the rejection region in this case. We can further emphasize this by giving the p-value, and this is going to be approximately 0, but I'll tell you exactly what it is. Zero. So then on step 5, we reject H0. And on step 6, we would say at the 5% significance level data provide evidence that fitted model is required. Right. So very similar idea to the deviance. The only difference now is, again, the null hypothesis is that the minimal model is sufficient. So rejection in this case would indicate the fitted model is needed. Whereas with the deviance, it's sort of the opposite, right? Where it is the opposite in terms of the result that would imply the fitted model fits well. Okay, so now we can look at the AIC. So the AIC is -2 times the log likelihood pi hat given y plus 2p. Okay, so I had mentioned before that one of the things with using AIC and BIC is having a very clear understanding of what your algorithm is doing in terms of finding the MLEs. So we have maximized the likelihood. So our likelihood curve is going to be something that has a mountaintop rather than a valley. So we have found the maximum point on that surface. The first thing we're doing here is multiplying by -2, okay? Which means that we are taking our mountain and we are flipping it upside down. So now we have gone from a peak to a valley. So that's why we are adding the penalty. This technically would be the same thing as taking the log likelihood and subtracting or multiplying by 2 and then just subtracting 2p. So you're at the valley and then you just push it down a bit. It's the same idea. It's just that in this particular context, they want to have a positive value. So the log likelihoods are typically negative. So they're multiplying by the negative to make it positive. And then you can compare the positives. So we have flipped the curve upside down, which means that the minimum value is best. And then we have added a penalty. So when we're using AICs of this form, we're looking for the smallest AIC. That would indicate the best fit. The other thing with this term is that the likelihood, at least as it's computed through software and whatnot, is including that combination term from the model. So this would actually be -2 times -186.235 plus the 167.5203. Okay, this value here is the sum from I = 1 to n log ni yi. And we talked about this yesterday in lab, and this is just to clarify how it's working in R. So we have to standardize by this term essentially. I'll just confirm that value really quick. And then this is going to be plus 2 times P. Okay, and this is going to give us 41.43. Right? But again, this value is only really going to be helpful to us in the context of model comparison. Right, and then the last value, just try and squeeze it in here, would be the BIC. Very similar computation compared to the AIC. So with the BIC, we have -2 pi hat given y plus p log n. So this is going to be -2 minus 186.235 plus 167.5203 plus 2 log 481. Sorry, and I'll just fill this part in as well. 2 log 2. And this is going to give us $49.782. All right. Cool. It's also worth pointing out, right? Like, it's also worth pointing out that when we're using, the reason that I'm showing you the adjustments is because when we're working with R, they give you the values that include this combination term for the logistic model. So the purpose of this exercise is just to make sure that you can work back and forth between the output that you're going to be using on assignments and for the project and the theoretical values. You could, for example, take the adjusted log likelihood value, so the value that's being used in the AIC, and you could use those within the pseudo r-squared calculation and within the value for C, because they're all just being adjusted by the same constant and the result should be the same. But I'm just trying to give you the full picture of what's happening compared to the theory that we've been talking about and in the software. Any questions? All right, so we've now seen a number of different model evaluation tools that we can use for comparison and we can use to assess fit. So we're trying to paint the same picture of how to diagnose our GLMs and use a foundation that we established with the linear regression model to understand where these different components would fit in, right? So again, with linear regression, we have terms like r-squared, adjusted r-squared. We had F statistics to evaluate goodness of fit. With our GLMs, we have the pseudo r-squared measures. We have the likelihood-based criteria. We have deviance. We have little c, or we have capital C, all serving a very similar purpose to the terms that we had established before. Now, with GLMs, we can compute residuals as well. The two common types of residuals that are used in generalized linear with fitting generalized linear models are the deviance residual and the Pearson residual. Both of these terms are basically just the components that make up the deviance calculation and the Pearson chi-square calculation that we looked at earlier on. So you can see, for example, the residual for the Pearson value, which is labeled E subscript I x squared. This is just the individual components of the x squared statistic square rooted, right? So we have yi minus nk pi hat, should be an I. So yi minus ni pi hat, we defined this before, divided by the square root of ni pi I hat 1 minus pi squared. So these are the values that we had seen when we introduced the chi-square value earlier on. So if we square each of these terms and add them together, we would end up with the x squared statistic. Our deviance residual calculation is basically just the components of the deviance. And we have a multiplier outside to determine the sign of that value. So we have the sign yi minus y hat. So this is going to be a negative or a positive, depending on the difference, multiplied by the square root 2 times yi log yi over yi hat plus ni minus yi log ni over yi divided by ni minus yi hat. These values in R are very easy to compute. They're done through the residual command. So you can specify whether you want the deviance residual or the Pearson residual. We'll also see how to calculate them by hand in lab next week. So we have the reference point. The only thing that's annoying about calculating a deviance residual by hand is that there are terms. If the yi's are 0, you end up with a log 0, which is an NA and R. So you have to compensate for the fact that it's an NA and set it basically to be equal to a 0 term. The yi out front should take care of it, but the problem is, like, when you multiply an NA by 0 and R, you end up with an NA. Anyways, I'll show you what I mean next week when we're in lab, but both of these are the standard residuals that are typically utilized for GLMs, and we can actually use them in a pretty familiar way. Before I describe that, I just want to talk very briefly about the idea of standardizing these. So we can standardize the deviance and the chi-square residual using the leverages, where the leverages are the diagonal elements of the hat matrix. Just like we had for the linear regression model, the hat matrix here is pretty much of the exact same form, except we have the weight matrix W being included in the calculation. So these leverage values are just the diagonal of the matrix, and we can use these to standardize both the deviance residual and the chi-square residual. So we can use these values to assess the fit of the model in a very similar way to how we did with linear regression. Again, the distributional assumptions that are attached to these values are conditional on having a large enough sample size. But for example, what we can do is plot the residual value against the explanatory values and use those to check for linearity. So if we have like a cloud-like shape, that would be the ideal situation. We can plot the standardized residuals on a normal QQ plot. They should be approximately standard normal distributed. So you would be looking for the straight line pattern there. I'll talk more about those a little bit later. We can also plot the residuals in order to see if there's evidence of a trend, and that would indicate a correlation. I have a few different examples of using these plots a bit later on, and I'll show you how to generate the plots in R. It actually is very similar to how we would generate residual plots for the standard linear model. So you can just type plot of the fitted GLM and it'll produce the plots for you. And most of the plots are exactly the same. For example, you can get Cook's distance plots. You get your QQ plot automatically. You would get a plot of the residuals versus the fitted values, for example. And you can use those in pretty much the exact same way you did for the linear model, because assuming that the sample size is large enough, again, the standardized residuals should be approximately normal. And the relationships between the residuals and the fitted values, or the residuals and the explanatory variables, should follow from what we had seen with the linear model. Okay, so again, as I had just mentioned, we do run into an issue. So for example, if we're fitting a Bernoulli model, we're really confined in terms of how we assess the model to those deviance and chi-squared assessments. But even in that case, as I mentioned before, these aren't really isotopically reliable. So you might have to, in that situation, use things like AIC and BIC and compare to other fitted models to try and get a sense of how well the model is fitting. I mean, that's pretty much the main point. So, so basically, like, if you have a large enough number of trials at each observation value, you can use these plots in the same way. If you do not, you restrict how you can assess the model, is the point. Okay, so we're going to look at an example where we're going to compare the different types of binomial GLMs, and we're going to go through calculation of the residuals and that sort of thing. I'm just going to make sure. Yeah, so first what we're going to do is look at an illustration of computing the residual values. So we're going to look at a demonstration of what I had just discussed. Then what we will do is talk about one of the issues with deviance in terms of assessing the fit of a binomial model. And then we will look at an example where we compare them. So I'm trying to keep this fairly linear. All right, so to illustrate the residuals, we're going to use the senility data. So this data set gives the Wechsler Adult Intelligence Scale value. So this is a score and a value of 0, or 1, representing whether or not a person is experiencing symptoms of senility. So we have 54 people in the data set. We have 54 WAIS scores, and we have 54 binary responses. All right, so we want to model the binary response as a function of the WAIS score. So again, we have a simple logistic model here. So the binary response is going to be, or the binary variable is going to be the response value. So this is a binomial with n equals 1 trial size. So that is going to mean that in the original formulation, we have a Bernoulli situation. And then we have our WAIS scores for each of those different observations. Right. So we actually are going to consider a grouped version of this data set. For right now, you don't need to worry too much about what this means. I'll show you how I constructed this in the lab. But we basically just reduced the sample size from 54 to 17, and we turned each of the observations into a binomial random variable where we grouped based off of the WAIS scores. Okay, and then I'll show you how this turned out on the next slide. So the resulting logistic model is shown here. So this would have been fitted in the same way we discussed before. We can use the GLM function, though. We don't need to do this by hand. So we're going to estimate the probability of a person experiencing the symptoms, and then we can estimate the number of people that are going to experience symptoms based off of their WAIS score. And then we will show demonstrations of how to calculate the Pearson and deviance residual. And at the same time, I can explain the definition of a covariate pattern for each of the observations. Okay, so I had mentioned before that there are 54 observations in the data set. Each observation has a unique WAIS score and a 0, 1 attached to them based off of whether or not they're experiencing symptoms. So in this illustration, we're using a grouped version of the data set where we're grouping based off of the WAIS score. So we're kind of treating the WAIS score as a category, but then also allowing it to be an explanatory value. I think it's fair to do this with this particular data set because when you fit the logistic regression model, the natural interpretation is the change in log odds for a 1 unit increase in the WAIS score. So the WAIS score is a whole number value is a whole number value. So when you talk about the change in the log odds as you shift across the levels of that WAIS score, that has a lot of natural meaning for us because we're talking about a shift from one whole number to the next, and the scale actually is a whole number scale. Okay, so you can see in the first column of this table that I have X listed here. So these are the WAIS scores, right? Okay, in the second column of the table, I have Y. This is counting the number of people that have experienced symptoms at that particular WAIS score. Okay, so for example, here we have 2 people with WAIS score of 4, 1 experienced symptoms. So we've basically taken the data and changed it from a Bernoulli problem to a binomial problem. So you can see, for example, that at 14, there were 7 people. I'll just write it down. So there were 7 people with WAIS score of 14 and 2 experienced symptoms. Right? Does that make sense? So it's now a true binomial problem in that sense. So we've just sort of taken the data, we've used the explanatory value that's available to us, and we've made some adjustments to how we're visualizing the data. And it fits a little more naturally into the modeling framework now. And the other thing that's nice about this is we don't have a binary problem where each value is a 0, 1. As I had mentioned before, when you're in this situation, a lot of those residual or the usage of those residual plots and the deviance and the chi-square assumptions break down very easily because you have a sample size of 1 at each value. This grouping is allowing us to increase our sample sizes at a number of the different values, which is going to allow for those assumptions to be a little bit more realistic. Okay, so in the third column, we have the pi hat values. So this is the expected probability that someone will experience symptoms given the WAIS score. This is just computed using the logistic regression model. So this is the inverse logit of the fitted model at those various values of X. We looked at an example of how to compute these last time. And then in the fifth column, we have the YI hat values. So this is simply just N multiplied by pi I hat. Multiplied by pi I hat. So there's nothing really sophisticated there. And then in the third column, we have the EI square values, and then we have the deviance values. So I just want to take you through an example of how these are computed now based off of the formulas that we had established before. All right. So we'll do this for the first observation. So E1 x squared is going to be equal to y minus ni pi I hat divided by the square root n, or this would be n1. N1 pi 1 hat 1 minus hat. All right, so from the previous table, this is going to be 1 minus 2 times 0.7521145. So we actually have that value. And then this should be divided by 2 multiplied by 0.7521. Multiplied by 1 minus. Okay, and then that should be equal to negative 0.825 or 826, I guess. Right. And then for the deviance residual, we're going to have sine y1 minus y1 hat multiplied by the square root 2 y1 log y1 over y1 hat plus n1 minus y1 times log n1 minus y1 divided by n1 minus y1 hat. And then again, just as a reminder, the y1 hat is equal to n1 pi 1 hat. Okay, so then this thing is going to be the sine of 1 minus 1.5, and I'll just round a little bit to save space, 1.504 multiplied by the square root 2 times 1 log 1 divided by 1.504 plus 2 minus 1 log 2 minus 1 divided by 2 minus 1.504. Okay, and then that should be negative 0.766. Okay. Any questions? Okay, so on slide 22, I have a number of different plots that we can use to evaluate the model. The first plot is a traditional scatter plot. So this is showing the proportion of people with symptoms versus their WAIS score. And then the smooth line going through that curve is the fitted logit model. Okay. In the second plot, we have the residuals versus the predicted values. So it's important to point out here, you'll notice that the scale of the predicted values goes down to -4. So this is actually the value of the logit of pi I hat. So this is the residual, the Pearson residual. The default R plot type is Pearson residual. So that's the Pearson residual versus the logit, which is why the scale is so low. Right. And then you can see here that this basically looks like a random scatter of points, which is what you would expect to see from this plot. So this is giving us some evidence the model fits well, because again, this type of plot, you're looking for random scatter. On the next plot, we have the standardized Pearson residual versus the quantiles of the normal distribution. You can see that for the most part, this pattern is actually quite linear, but then there's a few observations that deviate from the pattern. So number 5 and number 11, maybe potentially implying that there's something wrong with those points. If we go back and look at the data set, we would have 1, 2, 3, 4, 5, 2 observations, 6, 7, 8, 9, 10, 11, 7. So 2 points that might be worth looking into on a further note. Again, for the most part, this seems to fit the data pretty well, but we do have some tail action that would imply a little bit of skewness in the upper tail. And then I've also included a residual versus leverage plot. So for the most part here, there isn't any evidence of outlying points. You'll notice that the Cook's distance measure is given. We've talked about the definition of Cook's distance before, and we can use the same definition here. So values that have a Cook's distance outside of 1 might be considered influential, but in this particular case, we don't have any of those. Right? So still able to make a fairly nice assessment of the fitted model given the calculated residual values. And for the most part, our interpretation of those values or these plots is the same as they were before. All right. Okay. Excuse me for a second. I will be right back. All right. So on slide 23, I'm basically just summarizing the verbal description I gave for the residual plots. But so we have a definition of what each of the plots are showing. And then overall, it doesn't seem like the model fit is unreasonable given an assessment based off of those residual plots. Again, in the situation where we're working with a binomial, where we're working with binomially distributed data and we have large enough case counts for each observation, these plots should be interpretable in the same way that they were for a normal linear regression model. And we can more accurately use the deviance in the Pearson value to assess the goodness of fit. But if we want to use our logistic regression model in the binary case, most of these values are no longer reliable, and we would have to default to the likelihood-based values in those situations. Okay. Right, so I wanted to talk about over dispersion and under dispersion. I'll give you the definition with the time I have left. So we have assessed, or we have talked about using the deviance to assess the fit of our logistic regression models. And the deviance, as you'll recall, is a value that we can use to test the null hypothesis that the fitted model is sufficient. There are many situations, it's very common, where the deviance score will not result in rejection of the null hypothesis, but it is still quite big compared to the expected value of the chi-square, which is the degree of freedom. So in many situations, when we're using the deviance to evaluate a fitted model, we would like the deviance to not result, ideally the deviance would not result in rejection of the null hypothesis. So the deviance wouldn't give evidence that the maximal model is required. And we would also like the value of the deviance to be close to the degree of freedom for the test, for the degree of freedom to its degree of freedom. When the deviance is larger than the degree of freedom, this is evidence of what is called over dispersion. And over dispersion refers to the situation where the variance of the observed response variable exceeds its theoretical variance. So in the situations that we have been looking at, we have been using binomially distributed random values. These should all be pi's. We've been using pi, not p. So in the situation where we are working with binomial GLMs, the variation or the variance of a binomial random variable is n times pi times 1 minus pi. So n times the probability of success times the 1 minus the probability of success. When the response variable has a variance, so an observed variance that's greater than the theoretical variance, this would be evidence of over dispersion. And this is typically represented through the deviance being larger than its associated degrees of freedom. When the variance of the response is less than the theoretical variance, then we call this under dispersion. And this would be represented through the deviance being less than its degree of freedom. All right. So there's a lot of different reasons why over dispersion and under dispersion can occur. So for example, model assumptions not being completely accurate, like independence between the observations, for example, clusters being present within the population. For example, these are common reasons that you can experience over dispersion. Theoretically, we can talk about the result of over dispersion, and I have a little bit of a proof that's shown here. But I think, yeah, so I think it's a little more than I can describe in 2 minutes though. So basically what we're going to talk about is what it means for over dispersion to occur from a theoretical standpoint. So in terms of the actual variance of the response, and then I'm going to show you how we can deal with it in terms of our R output. It's actually very easy to accommodate for. And what it ends up doing is adjusting the standard errors that are associated with the parameter values. And I believe it adjusts the deviance as well, but I can't quite remember off the top of my head. So I will stop here. Okay. And then just as a reminder, we have assignment number 2 due tomorrow. And then I'll post assignment number 3 either Friday or on Monday. And that's, I don't think is due until after the break. So there's quite a bit of time between them. And we'll also have our second term test on March 4th, I believe. So I'll send out some updates about that next week. And otherwise, have a good weekend, and I'll talk to you on Tuesday. Oh, and I have office hours tomorrow morning if anyone has questions.